Welcome back to the second video on my series on the energy-momentum relation. So in the first video, we discussed this postulate that the total energy of the system is equal to gamma times m naught times c squared. We also showed that gamma, the length contraction factor for relativistic objects, can be expressed as a function of momentum. Okay, so we're going to expand on this postulate a little bit today. A second condition of this postulate is that it must satisfy a low speed condition. Okay, it has to satisfy a low speed condition. And that condition is that the energy of a massive particle is going to be equal to half m naught v squared. So that's its kinetic energy, plus, I'm going to use a different color, plus m naught c squared. Okay, and we haven't seen this term before in any of my videos, and now we are branching into maybe the atomic, is what we'll call it, the atomic world. This informs us something about our model. This informs us that no longer are our particles just points. In the Newtonian world, objects are points with no size that have mass and speed and position, x, y, z. Now we are saying that the energy content of the system also is comprised of this atomic energy, and loosely speaking, we're talking about the atomic binding energy. So now we have an atom that has a nucleus. Let me draw that a little bigger with protons, neutrons inside. We have sort of a cloud, an electron cloud around the atom, where the electrons sort of appear in existence as they interact with matter. Obviously, interpretation on the quantum aspect of that. But yeah, this mc squared is what keeps this atom stable. This is a stable atom we're talking about, like maybe hydrogen or something along those lines, right? So H gas, right? Okay, so this is the mc squared, Einstein's famous mc squared. So we need to show this low speed condition. So because in our original energy equation, gamma is the only thing that's a function of v, or momentum, we are going to demonstrate the low speed condition, or the low speed approximation of gamma. So a Taylor series expansion can be used here, or Maclaurin series specifically. We're going to say that gamma p near p equals 0, which is valid for what we're trying to show, is approximately equal to, and we'll take the first three terms. It's going to be equal to gamma at 0 plus gamma prime at 0 times p plus gamma double prime at 0 times p squared over 2. Okay, so now we need to compute these derivatives. It's not too hard, so let's go through it. Let's just stick off to the side here. Well, what's gamma? Gamma p is equal to 1 plus p over m naught c all squared. Also, it's useful to note right off the top, gamma at 0 is clearly equal to 1 because this p over mc squared term dies away at p equals 0. Okay, so gamma prime is going to be equal to, the half comes down, you get a 2p over m naught c all squared, and then 1 over the square root. Well, it becomes negative half. The root becomes negative half, so it's 1 over the square root plus p over m naught c all squared. And if you guys aren't familiar with derivatives, I just search up some Khan Academy videos on derivatives, or there's a lot of really great content out there. 3 Blue 1 Brown's another great video series that done on calculus. Okay, so this is our first one. Obviously our p's cancel, sorry, our twos cancel, and we notice that this part here is just 1 over gamma, so it has sort of this iterative quality. So it's p, write it this way, over m naught c all squared divided by gamma p. Okay, gamma double prime, we're going to have to use the quotient rule. So because obviously, well, this is a function of p and this is a function of p. So let's use the quotient rule. The quotient rule, just to remind ourselves, when f and g are both functions of the same variable, is equal to g f prime minus f g prime all over g squared. Okay? So g, well, g is just gamma p. F prime is pretty easy because it's just a function of p, so it's 1 over m naught c squared, minus f is p over m naught c all squared, and then times g prime. Well, what's g prime? G prime, we just calculated it. It's right here. It's here. That factor on top gets squared, and then you divide by gamma p. Now, both of these terms need to be divided by gamma p squared. 1 over gamma p squared. Okay, because that's g squared on the bottom there. So this simplifies a little bit. We get 1 over m naught c squared over gamma p minus p over m naught c squared, and then all squared over gamma p cubed. Okay, so recall what we're trying to do here. We're trying to see what is gamma at 0. We know that's 1. What's gamma prime at 0? And what's gamma double prime at 0? Well, gamma double prime at 0 is simply going to be, well, this becomes 1, this becomes 1, and because p is here, this goes to 0. So gamma, actually let's write it over here on the side, keep it consistent. This is just equal to 1 over m naught c squared. And what's gamma prime at 0? Well, here's gamma prime, and it's a function of p, so clearly it goes to 0 because that p on the top causes everything to collapse to 0. So in our expansion we can say gamma p near p equals 0 is approximately equal to 1 plus, and then there's 0, and then it's plus 1 over, so I'll do the half first because it was halves, just so we don't forget that, half, and then p squared over m naught c all squared. Okay, so remember what our energy momentum relation is. It's epsilon equals gamma m naught c squared, and we're trying to show that low speed condition. Remember the low speed condition, low speed, non-relativistic speed, is half m naught v squared plus m naught c squared. So let's see if we get that. This is sort of a reverse derivation because I sort of gave you the answer first with our postulate, and we're going to show that it satisfies this low speed condition. So at low speed, we can see that plugging everything in, take our approximation of gamma at low speed. I guess I should use approximately equal to at low speeds. It's equal to m naught c squared. So that's good. One of our terms pops out right away. It's this one. And then we get a plus half. Well, the p squared stays on top. This is an m naught squared, and we have 1 on top, so we keep 1, and the c squareds cancel. This c and this c cancel. All right, so further, the last step is another really cool little feature here is that the momentum, if you recall, we derived in the first video, is equal to gamma m naught times v. Now, at low speeds, okay, this is all, the blue is kind of the low speed approximation stuff, approximately equal to MOV. So we get E is approximately equal to m naught c squared plus 1/2, and then we get m naught squared v squared over m naught, and sure enough we get that that is equal to 1/2 m naught v squared plus m naught c squared. Okay, so this is certainly good news. This means that our energy momentum relation is satisfied at low non-relativistic speeds, and it gives us the answer. Certainly in the kinetic energy term, it gives us the answer that we expect from the laws of physics. And then this constant term is attributed to the model that we are now considering, that the nucleus is stable and has binding energy that overcomes the Coulomb force or some of the repulsive forces that would also exist in that model. All right, guys, thanks for watching. Please like and subscribe, comment below if you have anything to say about this, and we will continue it next time.